All right. Good morning. So I want to talk about Hilbert space. This is the space, all these things we have seen is taking place, the space of quantum mechanics, if you want. And I also introduced something called observables. So let me first start with Hilbert space. It's going to take some motivating. So what did we do so far? So far what we have seen is like we formulated so-called wave mechanics. So that was like a partial differential equation, which is the Schrödinger equation. We solved it, and we didn't ask questions, right? We said, this is what it is, we can prove it, and the attitude was like, let's just solve it and see what it gives us. And that's, I think, exactly what Schrödinger did. So this is, if you want, like a branch of mathematics, which is like, right, partial differential equations, which was very mature during the time of Schrödinger. And he was like a senior physicist, he knew very well all of these techniques. But you may have noticed, this is not usual partial differential equations, right? The way we do things, like, for example, any mathematician who sees that is going to have like headache. Right? It is not like well established from a mathematical point of view, and the whole point was to make it work. To make it work so that experiments can be explained. So this was like different, a little bit different from like mathematical partial differential equations. And there was also the question of wave function, right? There was like, we wrote this Greek letter psi, and then even Schrödinger in early years, I think he thought this to be like electron density, right? It's like some charge density. But later, it of course didn't make sense. The correct interpretation came from Born. Born said this is like a probability amplitude, and then he introduced a new branch of mathematics to the table, which is probability. Right? So each of these is like huge areas in mathematics. They are like specialists in the next building. They are only working in one area like this. And this probability introduced by Born was also weird, right? It wasn't like probability in the sense of mathematicians use. Like we had like typically in probability we have some probability P. In quantum mechanics we have P equal to psi squared. And to calculate things we split this psi star psi, and put things in between. Right? This is completely made up. Right? So this is also like not like in the mathematical sense very formal way, but again the point was to make it work. They were just making things up. And lastly, in parallel to this, there was also Heisenberg, and he introduced what is, I think it's kind of like an old terminology, but it was called matrix mechanics. Right? So wave mechanics versus the matrix mechanics. And according to the story that I've been told, Heisenberg wrote his equations and he had no idea about matrices. And he got some results that were like perfectly matching to like spectra at the time. And I think his advisor was Born. He showed it to Born, and Born said, Heisenberg, these are matrices. Right? He had no idea about matrix, and he invented all these things by just trying to understand the experiment. And I think this is also motivating for me, because most physicists I see, they try to learn mathematics to learn physics. I think that's, in my opinion, not the right way. You learn physics, and if necessary, mathematics comes along, in my opinion. But so this matrix mechanics was also introducing a new branch of mathematics to table, and it was linear algebra. Right? You are basically like whatever ammunition you can get, you just put it in work just to solve the problem. And I think that's what the spirit was in the day. But again, we are going to see this linear algebra is also weird. Like probability and PDEs, the linear algebra also has to be a little bit different. And it has to be, it says to take place in a different kind of space. It is not Euclidean space as you are used to it. It's going to be called Hilbert space. Good. And later, I think not long after, I think Dirac recognized what Heisenberg was doing. Okay, actually, again, some historical notes. People say there was also like some friction between Heisenberg and Schrödinger, right? Like they had like two competing theories, and both thought like their own theory was better, and they didn't like the other one. But Dirac showed, and if you read history, they say really nasty things for each other. I mean, for each other's theory. They are saying it's like nonsense and blah blah. But Dirac showed that they are actually exactly the same thing. And then we had like a unified, like of course unified in quotation mark, theory that we use even today. So Dirac and modern quantum mechanics. I also have to note there are other formulations of quantum mechanics that are also like identical to these two. There are many, but one of my favorites is path integral, and it came I think 30 years later due to Feynman. And it also has, right, it is also not mathematically well established. I don't think any mathematician would like what they see there, but it also works. And it's, for some problems, it has advantages. And especially if you are studying like complex many-body problems and field theory, what you do is you do quantum mechanics, but you do quantum mechanics in path integrals. But if you want to solve particle in a box, or if you want to solve hydrogen atom, for example, path integral will not give you much. You are going to be like torturing yourself. And there are others. If you keep reading, you are going to see there are many other approaches to quantum mechanics. Good. Then the key object was, so okay, number one is this psi squared. We said we have to work with psi squared, and it was a probability due to Born interpretation. And if this is a probability, right, for it to be like a meaningful probability, it should better not diverge. Like if you add all probabilities, you had one. And from that point of view, we need to have this thing to be finite. And that's what we call square integrable. So this is the space we have to work, right? We have to work in a space where functions are square integrable. Or we also call it normalizable if you want. And once you have this object, right, you can calculate any observable. And the way we calculated observable was expectation values. Any operator O, which can be a function of x on p, the expectation value calculated in this strange way. You just split psi, you put O in between, and you put the other psi. For example, from here, we calculate, for example, if you define a momentum expectation value, which is d over dt m expectation value of x, we found this to be equal to dx psi star minus I h bar d, let me use partial del x psi. And from here, we saw that what we call momentum is actually like an operator, right? So this is p. We have done this in the class. So this is minus I. Let me put ahead. And lastly, how do we find psi? And how does psi evolve in time? It evolves according to the Schrödinger equation. I h bar del psi del t is equal to h psi. And so this is what we called time-dependent Schrödinger equation. And if you like separate the variables, we found h psi is equal to e psi, and this is time independent. So now we want to formulate all of these things in the language of linear algebra. So in linear algebra, we have like some, if you want, I'll call it column vector, which is a1, a2, dot, 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 an. Right? This is an element of what we call Rn. And we can introduce an inner product. I think typically mathematicians use this notation for inner product. Let me also put square. Sometimes they don't put square, that's implied. It is A transpose dot A. And if you spell this out, you are going to find sum over I is equal to 1 to n, AI squared. And in this space, we can introduce so-called matrices or like operators. Like there's like something M. And if this M is acting on A, M, A is also an element of Rn. It is also a vector in the space. And from here, we think about M to be like a matrix with n times n elements, like m11 dot dot dot, m1n dot dot dot, mn1 dot dot dot, mnn, right? So the vectors in the quantum mechanical space, actually Dirac invented a very like intelligent notation, not to write all of these ugly integrals and all of these things over and over again. He introduced so-called bracket notation. Let me bracket. So he said, exactly like in the linear algebra, we can have column vectors in quantum mechanics, and we may have to transpose them to take inner products, right? And here he introduced, for example, some vector in the Hilbert space. This is F. This is transposed version. Some vector which is like column vector, which is the original version. And right, a testimony to what I claim that these things are invented, he just called it bracket, right? This is like, he split this word, he called it bra, and he called this one cat. Like very playful, but it makes things very easy for us. Exactly like Einstein's summation convention, right? Who wants to write sum and in this every time? Like these are smart people, they don't want to have like finger spasms writing all of these things. And they cannot copy paste like us, so. Or like similarly, think about Newton, right? He invented calculus and he was like, okay, I'm not going to write limit, something goes to 0, something minus something divided by. He didn't want to write this entire thing over and over again. He just said, okay, here's f prime, right? Just like that, Dirac invented this thing. And from here, we can write, for example, inner product. So inner product. So this is inner product between function f and inner product between function g. Both f and g are square integrable for this to be meaningful. And the definition, this is a definition, you take the integral dx from minus infinity to plus infinity. You take f star x and g x. Right? The transpose version comes with a star, original comes with itself. And now you can, if that's your thing, and if you have the appetite, you can do some mathematics here. You can, for example, prove if f is, so we had previously Rn, but quantum mechanics is not, some quantum mechanical models are going to be taking place in Rn. But generally, the things we have seen so far are taking place in Hilbert space, and I'm going to use this H here. If f is in H, and G is in H, then that means f, now I don't have to write this integral, this should be square integrable, and G, this should be square integrable, right? How nice, right? We don't have to write all these ugly things, we don't have to read those things. Now we can also think about what happens if we switch this thing, right? Let's think about this. If you switch this, here I have fg, I can also think about gf. What is this? This is dx, write the first one, g star x, write the second one, f of x. But if you compare this thing, if you compare this line with this line, you can see if you conjugate this expression, you get this expression, right? Here I have g, here I have g star, here I have f star, here I have f. Then this immediately shows me this thing is equal to fg complex conjugated. Good. So this is, let me box this in, sometimes useful. Okay. Suppose now let's think about what else we can get from linear algebra. Suppose f and g are like this square integrable and also non-zero functions. Then we can have let me first write it with linear algebra case first. So in linear algebra, if I have two vectors, and if I take them like this, take one and take another one, and if this gives you 0, we say that A1 is orthogonal, it's like perpendicular to A2. And we can also have something like this in quantum mechanics. If we say f g is equal to 0, and both f and g are non-zero, that's the interesting functions we are thinking about. We are not thinking about zero functions. Then we say f is orthogonal to g. Good. So again, let me continue the analogy. In linear algebra, we can have a basis, like any vector in Rn can be written in terms of an arbitrary basis, right? You can choose any basis you want, and it can be written like A1, E1, A2, E2, dot, 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 AN, AN, EN. And that means there is a set, E1, E2, dot, 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 En, we can do this, right? And this set has the property, if this set has the property Ei transpose dot Ej is equal to delta Ij, we say this set is orthonormal set. If you are not familiar with this language, don't worry, I think these are just words, and you'll be comfortable as you use it. And we want something similar in Hilbert space in H. Okay, it's harder to write this. We may have a set of functions, right? F1, F2, dot, 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 Fn. N can be infinite, but let me write it finite. It can also be finite. And any function in Hilbert space f of x can be written in terms of these. N, some coefficients. I used, I think, Cn, Fn. Right, this is kind of like Fourier series. And you can find, what did I use? Let me write it like this if you want. And you can immediately find what expansion coefficient is by taking a product with bra from both sides. So let me call it Fm, and let me call it Fm. And exactly like, for this to work, exactly like this inner product, right? This orthonormality, I want to require orthonormality here, like this Fi, Fj, delta Ij. Think about particle in a box. These are exactly the same things, but we are making it a little bit more formal. And this thing is delta Mn, and you immediately find that delta Mn is going to put this thing Cm. So this is Cm is equal to Fm F. How nice, right? We don't have to like take integrals and all of these things. Yes. Can you say one more time?
What's the difference between integral space and complex vectors?
So this is first. So far, we can also talk about complex space, but I'm thinking about like Rn here, like real n-dimensional Euclidean space. In some problems, that will be the Hilbert space. Like in some problems, we can use this to be the space. But in the more general case, the most general quantum mechanics problem, like particle in a box, harmonic oscillator, quantum well, all of these things, they are not taking place in Euclidean space. They are not taking place in Rn. So you don't have like, they are first infinite dimensional. And the vectors are not like this, right? The inner product in that space is not like this column vector times row vector. So we have this square integrable inner product. So we have to redefine everything we want, but as you see, most of the rules just carry over. But if you have like mathematical inclination, this is also a very deep thing, right? There are some branches of mathematics. There are like some pathologies with this. Like I'm going to talk about this in a little bit. When things are non-normalizable, like plane waves, then some of these things don't work, and you have to keep working. Good. And yes. So, like I said, okay, here is Rn, right? This is what we know from linear algebra. In the linear algebra, if we take the inner product, we have this orthonormality. Then I say, I should have the same thing in Hilbert space, right? I'm just not proving anything. I'm just saying that reasonable people expect reasonable things. Hilbert space should also have a complete set, and I should be able to expand functions in this set. And this set should also have some property like this, something like this is mapped to this. I'm just like copying my information from linear algebra to here and saying what it gives me. And yeah, once you understand this, like once you have this, you don't have a problem with this, right? This one is trivial. I say, okay, f can be expanded like this, and I say, let me multiply both sides with fm. I put fm here, and there's like a series of terms here. Each one I multiplied with fm. And when I multiply them with fm, I see that I have this orthonormality condition, and that gives, when I see this, I'm happy because I get rid of some and I get rid of this. And then at the end, this gives me fmf on the left-hand side and cm on the right-hand side. From here, I say cm is equal to fmf. Is that the question?
Yes, but how did you turn cm to cm?
Oh, because, so this is delta function, right? This is delta m.
can be changed.
Yes, exactly, right? So this one is saying that whenever m is equal to m, take it, and if it is not equal to n, throw it away, because this thing is what? This thing is, if m is equal to n, 1, if m is unequal to n, this is 0. Every time m is not equal to n, I can throw it out, and whenever m is equal to n, I can take it out. That's here. Right? That's the trick we like, because when we see this, exactly. And this saves us from both summations and also like delta function. Good. Any questions? Like in my opinion, like you'll see, like almost everything in this chapter is trivial, right? But if you don't look at it with the right mind, it's really confusing. Even for me, I get myself confused all the time. So let me introduce observables. So if we have like a function in Hilbert space, and if you have an operator, let me just keep it abstract at the moment. An operator is acting on this cat, and then it's giving another element in the Hilbert space. That's what we require. Like an operator is a transformation on F, which gives another cat in the space. And now I can define something like this. G, okay, let me do it in 2 steps. Sometimes, rather than writing like this, you'll see this is trivial, right? When you write things like this, you know who is operating who. But if you are confused, sometimes we can write it like this. Now I know this is acting on F. And now I want to introduce a second notation. So this G, A, F. What this is saying is like this A is acting on F and giving us another cat in the space, and I am taking inner product of this cat with a bra in the space. And if I want to open this up, I can do this. So this is dx minus infinity to plus infinity. The first one comes with a star, and I write the operator A. If you want, I can try to be careful by putting heads, but I'll forget it. And then f of x. Now I want to introduce a definition. So the Hermitian conjugate so physicists, I think, tend to say it Hermitian conjugate. Mathematicians, I think, sometimes call it adjoint. Whichever you want, you can use it. Of A is shown with, I could say like Hermitian conjugate of A, right? But we know notation, like good notation matters, right? Good notations enables good calculation, and it provides you like tools to avoid mistakes. Rather than doing it like this, we just call it A dagger. But this also may differ with mathematicians. If there are any mathematicians here, sometimes they use different notations. But physicists use this dagger notation. So Hermitian conjugate of an operator A is shown with A dagger, and it has the property let me copy this. It has the property, this equation. You can think about what we did with A plus and A minus in harmonic oscillator, right? We did by parts. We can do it with almost any operator. We can carry this to here. But in the most general case, we can carry it like this. So this A, rather than acting on F, I can choose to act it on G, but when it acts on G, it needs to change a little bit. And that's the A dagger part. So this equation is definition of Hermitian conjugate. And if we want to get rid of these ugly integrals, we can write entire thing in the Dirac notation, this is going to be A dagger G F. Okay, so this is the definition of Hermitian conjugate. A here transforms to A dagger if it has to act in the bra space. Good? Yes?
So we can take this A joint form so that the observable can be moved out of between the functions. Why are we saying that it is kind of different from usual probability?
So at the moment, I don't say this is observable. So this is most general operator, which may or may not be observable, but I define a formal procedure. My formal procedure is, for any operator A, there is an A dagger defined with this equation. And then I introduce this A dagger to be Hermitian conjugate of A, or adjoint of A. This is just a formal definition. Now we'll come to observables and we'll see why we do this. Anytime you see A, carry it here and put a dagger on it. And you can do this for any operator. Any operator can have like a Hermitian conjugate. Now I will talk about expectation values and observables. Let's think about this and see why we do this. So, expectation values. Now this is Q, right? And let me first write what we wrote previously. This is dx psi star of x. This Q psi of x minus infinity to plus infinity. And in the new language, we can write this like this, right? In the bracket notation. So this one is psi. I am acting on Q with psi. And this is giving me a new ket. And this ket is taking inner product with bra. Right? So this is exactly the same thing, but we are familiarizing ourselves with this shorter notation. But the point is, so if this is an observable, we can observe it, right? This is observable. If we can observe it, it better not have anything like I inside, right? Because we cannot observe imaginary numbers. They exist in our head. In real life, there is no imaginary number. Therefore, this result should be real. Otherwise, right, it's not an observable. That means Q should be equal to its complex conjugate. Right? For any complex number, if it's equal to its complex conjugate, it means the imaginary part is 0. And we just saw F, G, if you do the complex conjugation, you get G, F. Right? Then I can like use this. I have this psi Q psi should be equal to its complex conjugate. What is its complex conjugate? Take this to this side, Q psi, right? I am using this. Like, take this to this side and take it like this. And this thing is equal to its complex conjugate. That's what I'm writing. If you want, I can write it in 2 steps. Let me. So I just write this complex conjugation. And from here, this is equal to that. Okay, is that clear? But now I compare this side. I compare this side and this side. And how did we introduce Hermitian conjugate? Something here comes to here as A dagger. And you can see something here came here as Q dagger. But rather than Q dagger, I have Q. And this immediately tells me Q dagger as an operator should be equal to Q. Good. That's what I mean. Trivial I don't think any physicist sits down and calculates and proves this, because it's like so like linguistically natural. But when we prove it, we get confused, because I don't know if I really have to prove anything. But you know, that's how things are. And the conclusion from this is observables are represented with Hermitian operators. So if you are talking about an observable operator in the quantum mechanics, it has to be Hermitian. Any questions? Maybe I can show you an example to make this a little bit less formal, and we can finish it there. Let's consider example. Like, let's try momentum operator. Right? We know what momentum operator is because we work with it. And P, like I introduced in the beginning of lecture, is minus I h bar d dx. And I want to think about sandwiching this operator between two functions in Hilbert space. Right? I want to think about something like this: f, p, and g. Okay. And this thing is minus infinity to plus infinity. The first one comes with, okay, let me write dx first. The first one comes with f star of x. P is minus I h bar d. The second one is g dx n of x. Good. Any problems? And how did we carry this to here? We said we can do biparts. Let's do biparts. So you are going to have minus I h bar f star of x g of x minus infinity to plus infinity minus, and this derivative is going to move here. Let me just shift it a little bit. This is minus infinity to plus infinity dx d f star dx minus I h bar g of x. Now we said f and g are in the Hilbert space, right? We are now being a little bit fancy. Like that means they are square integrable. If they are square integrable, as x goes to plus or minus infinity, they should better be 0. Otherwise, you cannot square integrable. You cannot square integrate them. That's why I will call it 0. Right? And here I am going to manipulate this equation a little bit. So first, you can see there's like a minus I and minus I. Let me just copy and show you. I'm doing honest calculation. So let's erase this minus and this minus, so this is I. And I want to absorb this I h bar inside this conjugation, right? So here I will write this as I h bar d dx minus f complex conjugate, right? Is that okay? But I see that this is also P, right? Minus I h bar d dx is P. Then this immediately tells me, so this thing is P now acting on not G but F. And this is G. And I compare this line, right? I compare this line with this line. An operator acting to the cat is carried to an operator acting to the bra, and it is exactly what it is, right? There is no difference. From here I see P dagger should be equal to P. And that should be the case because momentum is on observable. We said observables should be Hermitian operators. So at more, it doesn't help us anything. It's just an observation. We are observing that we have observables in quantum mechanics, and these observables needs to be real. And this immediately tells us the operator is Hermitian, right? So that's just an observation. What benefits it brings us, we don't know yet. It will take a little bit getting used to. I want to slow down, but you'll see Hermitian operators has very nice properties, and they make our lives very easy. But we'll get there maybe in a couple of lectures. Good. So let me give you an exercise, and I want to show you one last thing and finish it there. So with the same spirit, please sit down and convince yourself. Exercise. Like I said, these things may look trivial, but if people ask you to prove, you may not be able to prove it, right? That's why we need to get out of our head and think about it objectively. So find Hermitian conjugates of, I don't know, like think about exactly like we are thinking about P, think about X. Position is an observable, so check if it is Hermitian operator. Think about complex I, right? This is multiplication with a complex. What is the Hermitian conjugate? Think about d dx. What is the Hermitian conjugate? Is this Hermitian operator? You can also think about d squared, dx squared. And a little bit trickier, think about this A plus. We actually did this in the class, but I think this is a good point for you to go back and do that calculation yourself to see what is the Hermitian conjugate of A plus. Okay? Okay, let me show you one last thing and I'll finish it there. So note, suppose I have a product of operators like F, A, B, and G. Now I think we can do this calculation without going to integrals, right? There is no benefit of integral, right? So this is like, take G, act on it with B, what comes out? Act on it with A. And I want to find the Hermitian conjugate of this thing, right? I can carry first this piece. So this is A dagger, now acting on F, B, G. Right? I took the first piece out. Now I can take the second piece, right? B, I can also carry it over. It's equal to, right? This thing comes to the beginning and becomes dagger. B dagger, A dagger, F, G. But this entire thing, I can think about this as a package, right? This package itself can go like AB dagger F G, and after comparing this line with this line, what I see is product Hermitian conjugate is B dagger A dagger. And if you want, I can also put the heads to say that these are operators. I think this also testifies, like, sometimes be careful, right? Things are trivial, but it's always good to be safe than sorry. Right? Take a moment to think about even the most trivial thing. I think this is like a very common mistake. People put A dagger, B dagger here. Okay? Any questions? All right. Thank you.